would like to thank the organizers for giving me the opportunity to speak here, and I hope that it will be educational and somewhat entertaining. I just wanted to say before I start that these images are all depictions of black holes, and hopefully I'll get to each and every single one of them. Okay, black holes. Now, although I advertised that it all started in World War I, it depends on one's perspective. And for me, perhaps the start of black holes as a physical object goes back to 17th century to this man. Danish astronomer Ole Rømer, who in 1676, by observing the delays in the eclipsing of Jupiter's moon Io, deduced that light had a finite speed. And he actually calculated it to be about 220,000 kilometers per second. This is quite impressive if you think about the result that we know now, which is 300,000 kilometers a second. And this actually went with the leading scientific thought of his time when people had begun that perhaps light does have a finite speed. And about a century after this, two independent researchers, one Englishman and one French, at slightly separate times, independently came up with the same concept of what happens if you have an object, a star that is big enough that light can't escape from it. This was first thought of and presented by John Michell in 1783 in a letter to the Royal Society, and independently written in a book by Laplace in 1796. And it's based on Newtonian gravity and the concept of escape velocity from the planet. So for something like the Earth, you can work out what the escape velocity is. Just use simple Newtonian gravitational formulae, and you work out that you need to be leaving the surface slightly faster than 11 kilometers a second to escape our planet. What these two gentlemen worked out is that you can do the same for any object you want, but let's make it really big and really massive so that when you work out the formula here, you get that escape velocity is speed of light, 300,000 kilometers a second. When that happens, no light can escape the surface. If there's no light coming from an object, it appears completely black. Hence, you have a black hole. But that's not what they called it. I believe they referred to it as a dark star. Now, this kind of gives you a conceptual idea of a black hole, but to truly understand black holes, you must understand Einstein's theory of general relativity, because black holes are general relativistic objects. And this brings us to Einstein. And basically, his theory of general relativity is what made Einstein Einstein, a household name recognized by almost every single person in the world. And it took him nearly 10 years to work it out. And finally, in November 1915, he published his results. And it was actually quite ahead of its time. And what general relativity does, essentially, it takes two different entities and puts them together. So it is a theory that describes the interplay between geometry of space-time. We're not going to talk about space or time separately anymore, it's space-time. Interplay of geometry of space-time and objects contained in it, more specifically matter-energy content of the space-time. And Einstein came up with a beautiful, elegant formula to describe all of this interaction that we call the Einstein equation. And what you have is, on the left-hand side, you have what you can think of as the geometry term, and on the right-hand side, you have what we call the matter-energy distribution form. And this is really all you need to understand the geometry of a given space-time. And Einstein himself actually used this to understand the geometry of the entire universe itself, where he modeled the distribution of matter as particles of dust uniformly distributed all around you, and then actually got the result that the universe is expanding, which is accepted universally today. So that's the Einstein equation. Interestingly enough, it wasn't Einstein who predicted black holes, it was another person, and it was this gentleman, Karl Schwarzschild, and he did it very soon after Einstein published his theory. And more remarkably, he did it while fighting at the Prussian front during World War I. In December 1915, he sent a manuscript to Einstein showing his work. Einstein was very impressed, and he took care of the publication of the work. And it was thanks to Einstein's kindness that Schwarzschild today has been given credit to something that has made him a legend in the circles of physics. His name has been attached to more than 10,000 papers, his solution. And what has he found? Well, he looked for a very simple solution to Einstein's equations. He said, okay, let's find a spherically symmetric, static vacuum solution. So, spherically symmetric means you sit at the center and you look around in all directions and everything looks the same. Static means everything looks the same for all time. And vacuum means he just ran to Einstein's equation and set the right-hand side to be equal to 0. And this is what he got, this thing here that we call the Schwarzschild metric. It is basically a measuring stick that we use in curved geometry, and it measures distances between events in space-time. So no longer space, but space-time. So you can think of this in understandable terms as us living on the surface of a sphere on Earth. Our geometry is actually curved. And on the surface of a sphere, you can't measure distances with a meter stick, right? Because the surface is curved. So you come up with numbers to locate yourself, latitude and longitude, and then you would use the metric for a spherical surface and calculate distance, say, between Dublin and New York. Well, Schwarzschild did it for a four-dimensional space-time, and this is what it looks like. The interesting thing about his solution is these two terms. At a given radius that equals 2m, that we now call the Schwarzschild radius, these two terms are 0. And that gives you a very interesting surface. And what people found out is that light emitted from within this radial distance of 2m is never going to leave the surface. It's forever trapped inside the sphere with radius 2m. And this means that events that happen inside the sphere are forever hidden from outside observers like us. So this surface has come to be known as the Schwarzschild black hole. Now, m here is a free parameter of the solution. It turns out that there is mass of the object involved. But if you wanted to know what it is in terms of distance for something that has the mass of our sun, it translates to 3 kilometers. So this is in 1915, but this was way ahead of its time, and it wasn't very well received, because at that time only about a dozen people understood general relativity. It took nearly another 15 years for Schwarzschild's construct to get some support, and this was done by a brilliant young Indian researcher, Chandrasekhar, who in 1930, at the age of 19, came up with what is now been given his name, Chandrasekhar limit for stars. What he found out is that if a star is massive enough, its gravity is so strong that it will crush the star once the star uses up all its fuel. So it's a balance between outward pressure from having a hot gas and self-gravity. And once you burn off all the gas, there is nothing to stop the gravity from crushing the star into a single point. So think about that. Something as big as our sun could potentially crush into a single point in space-time that we call singularity. It has infinite density, and we think the laws of physics break down at this point. So Chandrasekhar did the calculation, and today we know that usually, so this is for a type of star called white dwarf, but we know usually that if a star has more than 3 solar masses, once it dies, it will probably become a black hole. And his work got further support, mathematical support, about 10 years later by 2 researchers. I think everyone has heard of Robert Oppenheimer and Hartland Snyder, who together worked on a simplified, idealized model of a shell of dust collapsing under its own gravity. And what they discovered is that if you just let it go, it collapses to a single point, singularity, and it forms an event horizon. And the space-time outside, it becomes Schwarzschild space-time. Let's take a closer look at Schwarzschild's solution, because this is what most people think of as a black hole. If you put the black hole against the uniform background of stars, you would see something like this. You have the black hole. Now keep in mind that this is not like a hole in a wall. This is a spherical surface. So you would be looking at a dark sphere. And you have this fuzzy ring of light around it. And this is actually a special surface as well. Let me simplify this and let's look at a diagram of the space-time. So let's take the sphere, take an equatorial slice, and put it on a flat table. And now we're looking at it from above. We've already talked about the singularity, point of infinite density, where all the star's mass is located. We already talked about event horizon located at a radial distance of 2m. Inside the event horizon is where the black hole is, so have it as black. And then you have this other surface that we call the photon sphere at a radius of 3m. Essentially, what happens is if you have light being emitted from the surface of the sphere, 50% of it will get absorbed in, and 50% of it will come out of the black hole, but it comes out in a really warped fashion because the space-time around the black hole is warped. Then you have this red circle, inside of which you can't have stable orbits for planets or stars, outside of which you can. Now this is in a flat geometry, but we can't think of it in terms of curved geometry. We do something called space-time embedding. And so now I'm looking at my table from the edge, and instead of having a flat surface for the table, I have something that looks like a bit of a slide. And now let me add the rotational dimension back onto this. So what I've done is I've taken my equatorial slicing that I put on a flat table, and I've basically now redrawn it in something like a base. And you can see where the curvature is now. It kind of becomes evident. Things that were straight lines on the table will now be following this curved surface. So if I took a marble and just flicked it off, it would just kind of curve around and maybe fall in. So this is a way of visualizing curved space-time. Now let's look at a nice video that shows what light does around the Schwarzschild black hole. This is Earth orbiting a black hole of the same size, so the black hole would have a radius of about 6,000 kilometers. And you can see that the image of the Earth is doing fairly unexpected, crazy things. It's getting split up, it forms a ring, which is known as an Einstein ring in his honor. These are all things that we know happen around black holes, but they also happen around massive galaxies. We've actually observed these rings. It's called gravitational lensing. And the thing to notice here is that as the Earth comes towards us, it turns blue, and it goes away from us, it turns red. That's called blue shifting and red shifting with the frequencies. And one thing I want to mention is that here we've done something unrealistic and turned off the tidal forces due to the gravity of the black hole. So normally if you have the Earth orbiting a black hole this close, and this translates to that dashed red circle that I showed you before, so the Earth is sitting on that circle. The tidal forces of the black hole will tear the Earth apart, and all you have is a ring of particles like a ring around Saturn that slowly fall in. Now Schwarzschild's solution has given us amazing physics, but what we want is a black hole solution for rotating objects. And this was the holy grail of general relativity from 1950 until it was found by this man in 1963. And the reason for this is simple. If black holes are collapsed stars, or they can be collapsed gas, all these things rotate. And when you take something like the sun, which is 1 million kilometers across, you make it 3 kilometers across, the sun spins around once every 25 days. That spin rate will become something like hundreds to thousands of times a second. So with black holes that we think exist in the universe spin. And Roy Kerr found the solution in '63, and in his honor we usually call the black holes Kerr black holes. And they come with a plethora of very interesting phenomena. For one, a Kerr black hole has 2 horizons, not one. An inner and outer horizon that are separated by some distance. But what we call the event horizon is still the outer horizon. So anything inside this region will actually be black to us. More interestingly, the singularity that was point blank for a Schwarzschild black hole is now a ring. We call it a ring singularity. And if you can see it here, you can't read it, but the singularity, the ring, has a radius of r equals 0. So I'm talking about 0 radius ring. How can that happen? It happens mathematically through something called analytic extension. And basically the region inside the ring is a region of negative radius. And in physical terms, this actually means that this black hole gives you a gateway to another universe. So you actually have wormholes inside Kerr black holes. So let's now focus on this blue trajectory here. This is a person falling into a Kerr black hole, and the ring singularity is depicted by this vertical line here. And what happens is, this region is what we call the wormhole. So if you were here, inside the black hole, inside the event horizon, you're in this region, and what you're looking at is, this is another universe. You're looking through the ring, through the wormhole to another universe. That's what's depicted in purple here as a white hole. This is before you fall in, and this is after you fall through and you're inside the other universe and you're looking behind you and seeing where you came from. And you can actually do this without getting killed if the black hole is big enough. It goes back to tidal forces. We're not done yet. There are also other interesting phenomena. So the rotation is so large around the curved black hole that it actually drags space-time around it, okay, like a whirlpool. Imagine looking at your bathtub and seeing the water whirlpooling. Now imagine that for space-time. It doesn't just happen for space, it happens for time. This means that there's a very special region around the rotating curved black hole that we call the ergosphere. And if you're inside this region, no matter how powerful a ship you have, you just get dragged around as the black hole rotates. And this is called the stationary limit, the limiting surface of ergosphere. And this is kind of what it would look like in terms of looking from above. But we're not done yet. There are still more things coming up. We've talked about gravitational lensing already around Schwarzschild black holes, but it is actually even more extreme for curved black holes. For one, a curved black hole is smaller in size than a Schwarzschild black hole for a black hole of the same mass, which means you can get closer without falling in, so there's more curvature of space-time. And two, there is now an asymmetry for those of you that can see this figure, but it's no longer a sphere, but it's flattened on the left-hand side. And this happens because of the rotation. So in this image, the black hole is rotating such that the left side's coming out the page, and the right-hand side is going back in. And if you can read, the bottom here is tracking how many times you see the same image. And there is this one here is the 10th image of the same thing that's going around the black hole and finally coming out to you. This is actually taken from the book of the physicist who wrote the script for Interstellar, Kip Thorne. And now let me show you what that looks like, animated. This is animation made by the company that did the special effects for Interstellar, Double Negative. And here we're looking at a spinning black hole, curved black hole. And the spin is usually given in terms of a dimensionless number between 0 and 1. This black hole has a spin of 0.999, which means if you were sitting on the horizon attached to the black hole, you would be going around at a 99.9% of the speed of light. And you can kind of see stars being dragged around in the image. And the only thing to add here is that, oops, the image looks a bit rectangular because of the projection that the movie company used. They have much longer videos. If you're interested, take a look. But this is the only short one that I could fit into my slides. You get crazy orbits. No longer like the orbits you have in the solar system. Here's what they look like. In the solar system, you're used to mostly circular orbits. The plane stays the same here. The plane's precessing, the orbits getting close and far. It seems like it never closes on itself. But these are perfectly stable orbits. They won't fall in or they won't escape. Now, let's talk about the name black holes. It was hard to track this down, but it seems like the first person to use black hole in academic context is physicist Robert Dicke, circa 6061, and he got it from a historical event called the Black Hole of Calcutta. And this refers to a cell in a military prison in India, where in 1756 the Indian general locked up about 120 British soldiers in one single cell and let them fight it out during the heat of the day. And by the next day, only about 24 of them survived. And so that's the black hole. Although, according to the non-British sources, this is exaggerated. The first time black holes appear in scientific print, January 1964, in an article by Anne Ewing. Her impressions about this conference in '63. But I found that they actually appear earlier than that. For those of you that can't read this, let me read it to you. Confinement to the black hole to be reserved for cases of drunkenness, riot, violence, or insolence to superiors, British Army Regulation 1844. Whatever the original term, this the man is who is attributed for popularizing the term black hole. And he's done it starting December 1967 at a conference. But he doesn't take credit. When John Wheeler was asked where he got it from, he said a few months prior to December 1967, he was at another conference, and he kept referring to the black hole as a gravitationally collapsed object. And someone interrupted him and said, why don't you just call it a black hole? And we've been calling them black holes ever since. Now, all of this has been great, but what's the point of talking about mathematical objects if they're not really existing out in the universe. That's like string theory, but this is more interesting. So we actually think that we found black holes, and we've been looking at them for a while. One place where you can find them is binary star systems where you have an invisible companion. And the first one we found was in the constellation Cygnus in 1965. This is in our galaxy, not very far away. By 1971, we knew that there was an invisible compact companion around a giant blue star. Here's the X-ray source. By 1973, the mass of the invisible companion was measured, and it was agreed that it was more than 10 solar masses. So people said, it's small, it's very massive, it must be a black hole. And it's been accepted as one ever since. Here's what the system might look like. Giant blue star, black hole. What the black hole does is it sucks matter in from the star. That kind of falls in what's called an accretion disk. And as it's falling in, it heats up under its own gravity, under its own friction, the gas. And this white region around the black hole is the brightest and the hottest place, and that's where the X-ray emission comes from. Fortunately, we've launched X-ray satellites since the 60s, and we've actually found 400,000 X-ray sources already, confirmed. And thousands of these are such X-ray binaries as Cygnus X-1. And here's a sky map showing some of these. So focus on the red dots, those are the X-ray binaries. But it seems like we've already found hundreds to thousands of solar mass black holes. There is another black hole that exists in the center of our galaxy called Sag star. The center of the galaxy is next to the constellation Sagittarius. This thing has been there for a very long time. And we actually, by looking at the orbits of stars around it, we measured its mass, 4 million solar masses, so we think it's a black hole. Here's a movie showing the orbits from 1995 till 2013. So we look at the stars, we calculate what needs to be in the middle to make them go around this fast, and it's 4 million solar mass black hole. Fortunately, we think these supermassive black holes exist all over the universe, so there are hundreds of billions of them. And finally, quick talk about interstellar. I'm sorry I didn't do my timing very well. Gigantic black hole, 100 million solar masses. It's spinning almost at the speed of light. This is the only way they could get the 7 years to 1 hour time warping in the movie. And finally, let me go back to this. This is the best part. This is a real visualization of that accretion disk that I showed you. Although it is flat like this, in reality, yes, but when you look at it, it gets warped like this due to gravitational lensing around the black hole. And if you add extra realistic effects, like the fact that it gets redshifted and it gets less bright, the final product looks like this. But the director didn't want to do this. So there you have it. Thank you very much.
Thanks very much, Dr. Sarp. Do we have any questions? Yes, Richard, yes.
So you said big black holes were big enough you could go through them and survive. So that implies that supermassive black holes at the centre of galaxies, you should be able to go to a different universe. Is that right?
Yes.
So does everybody hear that question on this side? You heard it?
Yeah, that's actually very good. Supermassive black holes are exactly the kind of black holes you would need to go through the singularity without getting torn apart. They have to be extremely big because usually people think of the tidal forces destroying them at the horizon, but the tidal forces exist in all ranges. So it's just a matter of getting torn whether you're outside the horizon or inside the horizon. But if you make it big enough, and actually one page showed that we found some that are as massive as galaxies. Yeah, you could go through.
And when you say other universes, you mean like other universes? So like a whole other system, like a whole other thing?
Yeah, so at this point we're kind of getting into the, conjectural, hypothetical grounds, just like at the end of the movie Interstellar. Although, that was not a parallel universe, that was completely something else. Mathematically it has negative radius. That actually means that stuff's constantly coming out of it. So if you cross over, you'll never be able to come back again. And even if you could come back, you couldn't come out of the black hole anyway. So be careful. It's a one-way trip.
Any other questions? Any other questions? When you say we, you said it a lot.
Yeah.
Who is we?
Scientists in general.
Oh, okay. Is this your? So was this? Is this a culmination of a history line that you're particularly interested in, or is some of your work in this field?
So my work is specifically deals with looking at corrections to orbits of stars around black holes. For example, I showed you a movie where there was an orbit going around and doing all kinds of things, and I said it can stay there forever. That's actually incorrect. There's something called gravitational radiation. So just as when the electron spins, it emits X-rays, when two masses go around each other, they emit gravitational radiation, which means they actually get closer and closer to each other. And we've seen this in the universe. But this is not something we have to worry about in the solar system.
Oh, I could listen to you forever.